Welcome to Evolutionary Biology. Today, we are going to explore one of the most dramatic and transformative events in the history of our planet, the KT extinction. Imagine a thriving, bustling world dominated by giant reptiles, suddenly plunged into darkness and chaos. This single catastrophic event wiped out nearly 75% of all species on Earth, including all non-avian dinosaurs. But why does this matter to us? Because this dramatic reset button paved the way for small, furry mammals, our very own ancestors, to eventually take over the planet. Let us dive in and understand exactly how and why this happened. Now that we know what the KT extinction is, let us look at the specifics of the event itself. This mass extinction occurred approximately 66 million years ago. It was so severe that it wiped out 3/4 of all plant and animal species on Earth. The primary accepted cause for this unimaginable devastation is the impact of a massive asteroid or comet. This rock from space was roughly 10 to 15 kilometers in diameter, and it struck the Earth in what is now the Yucatan Peninsula in Mexico. The sheer scale of this impact instantly transformed a lush, warm greenhouse world into a hostile environment, triggering a global blackout that lasted for months. Understanding the cause of the extinction leads us to ask, how do we actually know this happened? The evidence lies in the geological record, specifically a feature known as the KPG boundary. This event marks the exact boundary between the Cretaceous and Paleogene geological periods. You might wonder about the name. The letter K stands for the German word Kreide, meaning chalk, referring to the Cretaceous period, while T stands for the Tertiary period, an older term for the Paleogene. Globally, this boundary is characterized by a thin layer of sediment that contains unusually high levels of iridium. Iridium is a rare metal on Earth's surface, but is very common in asteroids, providing the smoking gun for the impact theory. This geological evidence brings us to an important question. Why is this crucial for evolutionary biology? The KT extinction perfectly demonstrates how macroevolution and mass extinctions shape the entire tree of life. It teaches us about the extreme fragility of ecosystems and how sudden environmental changes can cause the complete collapse of complex food webs. When the non-avian dinosaurs were wiped out, they left behind empty ecological niches. This triggered a process called adaptive radiation, where the surviving species, mostly small nocturnal mammals, rapidly evolved and diversified to fill those vacant roles. Without this catastrophic reset, dinosaurs might still rule the terrestrial ecosystems today, and human beings might never have evolved. Before we move on to the biological aftermath, let us understand the physical force of the impact itself. To truly grasp the sheer scale of the devastation, we can calculate the kinetic energy released by the asteroid using a fundamental physics equation. The formula is E equals 1/2 m times v squared. Here, E represents the kinetic energy released upon impact, measured in joules. The symbol m stands for the mass of the asteroid in kilograms, which depends on its volume and density. Finally, v represents the velocity or speed of the asteroid relative to Earth, measured in meters per second. Notice that the velocity term is squared. This means that even a slight increase in the asteroid's speed results in a massive, exponential increase in the destructive energy released. Now that we have our formula, let us see this with a concrete example by estimating the energy of the Chicxulub asteroid. We are given that the asteroid had a mass of 1.0 times 10 to the power of 15 kilograms, and it was traveling at a velocity of 2.0 times 10 to the power of 4 meters per second. We need to calculate the total kinetic energy released. First, we substitute the mass and velocity into our equation. The crucial next step is to square the velocity term before multiplying, following the standard order of operations. Squaring the velocity gives us 4.0 times 10 to the 8th. Multiplying this by the mass and dividing by 2 gives us our final answer, 2.0 times 10 to the 23rd joules. This unimaginable energy is roughly equivalent to 100 million megatons of TNT, instantly vaporizing rock and triggering global tsunamis. This astronomical release of energy we just calculated leads us directly to the biological consequences. The immense kinetic energy was instantly converted into heat, shock waves, and massive tsunamis. But the most deadly effect was atmospheric. The impact threw billions of tons of vaporized rock and debris high into the atmosphere. This created a thick global debris cloud that completely blocked out the sun, plunging the Earth into a nuclear winter. Without sunlight, photosynthesis ground to a halt. The plants and phytoplankton died off first. Without plants, the herbivores starved. And without herbivores, the carnivores had nothing left to eat. This caused a rapid, severe collapse of complex food webs across the entire planet. Now that we understand how the food webs collapsed, let us look at how scientists actually measure this biological loss. In evolutionary biology, we use a quantitative approach to objectively compare mass extinctions. We calculate the extinction magnitude using this formula. M equals n sub e divided by n sub t, all multiplied by 100. Here, m represents the extinction magnitude, expressed as a percentage. The variable n sub e stands for the number of taxa, such as species or genera, that went extinct. The variable n sub t represents the total number of taxa that were present immediately before the extinction began. As the number of extinct taxa increases, the overall magnitude increases, indicating a more severe event. Multiplying by 100 simply converts the decimal fraction into an easily readable percentage. Let us apply this formula to a real-world scenario from the fossil record. Paleontologists studying a specific marine ecosystem found that out of a total of 1,200 marine genera present in the late Cretaceous, exactly 564 genera disappeared in the early Paleogene. We need to calculate the extinction magnitude. First, we substitute our values into the formula, placing 564 in the numerator and 1,200 in the denominator. Performing the division gives us a decimal of 0.47, which represents the raw proportion of loss. Finally, we multiply by 100 to convert this into a percentage. The final answer is 47%. Physically, this means nearly half of all marine genera in this ecosystem were completely wiped out, reflecting the severe collapse of the ocean's food chain due to the lack of sunlight. To fully grasp everything we have discussed, let us look at this diagram illustrating the KT impact and the resulting geological boundary. At the top of the image, you can see the massive asteroid striking the Earth, throwing up a thick atmospheric debris cloud that is actively blocking the sun. Below ground, we see a cross-section of the Earth's rock layers with time moving upwards from older to younger rock. The bottom layer represents the Cretaceous period, filled with the fossils of giant dinosaurs. Right above it is the thin, dark band representing the KPG boundary, labeled as the Iridium anomaly. Notice how the dinosaur fossils completely disappear above this line. In the top layer, the Paleogene period, we only see the fossils of small mammals. This visual perfectly captures the sudden, dramatic shift in life on Earth caused by the impact. Having seen the stark visual evidence of the extinction, we must also recognize the incredible resilience of life. By analyzing how life recovered after the KT event, scientists gain vital insights into ecosystem resilience. The sudden removal of the dominant dinosaurs left countless ecological niches completely empty. This vacuum drove the mechanics of adaptive radiation, allowing the surviving species to rapidly evolve and diversify. Furthermore, studying this ancient catastrophe is not just about the past. It helps modern scientists model the potential impacts of future asteroid strikes or severe climate change scenarios, teaching us how modern food webs might react to sudden, extreme environmental stress. We have covered a tremendous amount of ground today, so let us review the key takeaways. First, the KT extinction was driven by a catastrophic asteroid impact 66 million years ago, leaving behind the iridium-rich KPG boundary. Second, the unimaginable kinetic energy of the impact caused a global nuclear winter, halting photosynthesis and collapsing food webs worldwide. Third, this resulted in the extinction of roughly 75% of all species, a loss we can quantify using extinction magnitude calculations. Finally, and most importantly for us, this devastating loss of life emptied ecological niches, setting the stage for the adaptive radiation of mammals and the eventual evolution of human beings. You now have a solid understanding of one of Earth's most pivotal moments.